Hello. Okay, so real quickly, we're going to go over DSD, Digital Circuits and Design. This is a college level course. Let's see how far we can go. I've only done the notes for a few lectures. Let me just check if everything's working. Okay, everything is working. Let us go. Lecture number 1, binary digits. So we start off with basics, like literally the basics. Size is 1 binary digit is equal to 1 bit, 4 bits is equal to 1 nibble, 8 bits is equal to 1 byte. A binary bit is basically a 0 or a 1. It is, one of the numerous numerical ways to, well, display counting and all such. Then we have decimal, base 10, which we are famous on, which we already know. Binary is, well, base 2, decimal is base 10. This is what we use daily. Each position is a power of 10 units. This is how sort of like we can, let's say, convert from binary decimal to binary and use stuff like that. We're also gonna go over that, but right now it's just the basics, but we'll go on to that. Then we have binary to decimal. How to convert from binary to decimal. Multiply each by its power of 2, starting from the right. So that's one thing with binary stuff and all that. For instance, we have what would you call it, a number. Let's replicate this. We always have to start from the right, or always right hand side. So we have to start from the right hand side. As this example is given, let's just try to explain this, work on this. Let's just zoom in a little more. Give this go. Okay. We have 1, 0, 1. So how this will work is that to convert this converts to decimal, we have to do a few things. One other thing that is important to note is to indicate the bases. We write a small 2. For instance, if we have a base 10 number, then to identify it to the reader, we write it as, for instance, 27 to the base 10. If we have a base 2 or a binary number, then we can do 1, 0, 1, and we have to write this too. This is sort of like indicates us that it's either base 10 or base 2. We can also go further on. This isn't just limited to base 10 and base 2, binary and decimal. It's also for base 16 or hexadecimal, which is, for instance, 5F. I think that's how you do it. Maybe I'm wrong. Hold up, I think I'm wrong on that one. 5F, no, I think that's okay. That's okay. I don't know it off of heart, Anyways, so we have to convert this to decimal. So let's just change this up. Okay. You start from the right. We have 1, 0, 1, 1. And right on top of that, we write 2 raised to the power 0, 2 raised to the power 1. 2 raised to the power 2, 2 raised to the power 4. Let's make this neat, why not? You don't have to draw a table, this is like the easiest way to remember how to do it. I'm really sorry about the jagged lines, I don't know how to fix them, but you know, they'll get the meaning across. So we have this. After we do this, we need to see what digit corresponds to which number. It starts off always from 2. For instance, this is a 4-bit number. If it is a 5-bit number, then we will just add another one here. By the way, this is 3. I don't know why I wrote this. This is 3. This will be 4. If it will be a 5-bit number, we will add. Apology. We will add this extra bit, but right now we're only working with 4-bit numbers, so let's not add this. And the numbering always starts from 0. Yeah, it starts from 0. So now what we do is we take this, we turn 1 into 2 raised to the power 0. We take this plus 0 into 2 raised to the power 1. We take this, we do 2, 2, and 2. Let's make it, you know, symmetrical or in a sort of format. 2 raised to the power 2 plus 1 into 2 raised to the power 3. Just like that. And this will all equal to our decimal number. So 0, let's start from here. 2 into 2 raised to the power 0, that is equal to 1 plus 0 plus 4, this plus 8. And that leads us to having a 13 base to 10. This is converted, so this in binary equals to this in decimal. Let's just write that over here too. Binary, and this is decimal. Let's move on, and I think the next is talking about hexadecimal. Just give me a minute. How do I do this? Oh, God. What just happened? Just give me a minute, okay? Give me a minute. So let's move this just a bit, you know, just a bit here too. Why didn't get there? There we go. So we get a little bit more room. Next up, we have binary. As we stated, binary to hex. Hexadecimal is so hexadecimal is base 16. For example, we have what's written right here. That's too complicated. Let me think. What should we write? I guess 1E. Yeah. This will be hexadecimal. And again, always write 16 below so that we understand that it is indeed a hexadecimal number we are referring to. And next, we have binary to hex. Your notes show make groups of 4 bits. Starting from the right, again, we have to always start from the right. That's the rule. This is digital system and design, and although this is like basic binary, all of that stuff, you've already probably learned that from other syllabuses, but in here, going forward, we've obviously learned about what was it, system Verilog code, and how to overall design systems. We will this course, from what I'm teaching these notes, the syllabus that I'm following, it has me working with Vivado and Questasim, so I think maybe I'll probably do some working on that as well. But right now, let's go back to our current syllabus or current topic at hand. The example that it's given us is a 5-bit binary number, 1110, and this is how we convert it to hex. We split it down into 4 bits, into groups of 4 bits. What did we learn that 4 bits was? 4 bits is 1 nibble. But right now it's just calling it 4 bits because that's, I believe, more standard. The number that we have is 1 0 binary, but for calculations I'll remove that. We have to start from the right and add a few more. I kind of want to change my color. I don't like the color right now. I guess what I can do 1 2 3 4 3 4 0. So we have to start from the right and divide it into 4 bits. So this will be 1, but hey, what will we do here? There's nothing here. Our 2 only has 1 bit. Well, we fill in the remaining numbers with more zeros because zeros have no values. 1, 0. Because if we translate this into a decimal number, it will still be the same. So no difference. But now that we have this and we have this divided into 2, I think I forgot one. Yeah. Now we have this into 2 nibbles or 2 parts of 4. And then we can, well, basically convert this into hexadecimal. So there's a table that you have to follow. It's not right here. Let me just see if I can find the hexadecimal table real quick. Okay, so here is like the simplest one I could find. There you go. So these are binary numbers, and it corresponds to our decimal and hexadecimal numbers. The binary number, the hexadecimal numbers, they have 15 digits, you could call it. It ranges all the way from 0 to 15. Obviously, you have to include zeros in these number systems. So what we do is we see that 0001, 0001 is just 1. So what we do is we write a 1 and then a 1110. What will a 1110 be? After you get a hold of this, you'll probably be, maybe be able to keep this off the top of your head. 1110, which is right here. God, I can't. This is white on white, that's why it doesn't work. But anyways, it's going to be 14. But you're gonna write 14 because that's just like the decimal number. We're not looking at decimals, we're looking at hexadecimals. The hexadecimal equivalent of 14 is E, so we'll write E over here. This is the hexadecimal number. Now we have that down. Do one more thing right now. Let's just condense it all down. Again, I think we have to redraw the arrows again. I will like this and like this. God, no, we have to have the same color. This. Okay. Let's go one back. So we were. Let's show this. Goes to 4. We did this. Now hex to binary. We've done binary to hex, now hex to binary. The code that we are given is 4B. What to do? 4B is our hexadecimal code. I don't like this. I'm sorry, I'm going to have to change this back. Text pen. I don't want to use white. What else should we use other than white? Let's try a different color, I guess. Let's try this blue. Is there like a pastel color? I guess this will do. So now we have 4B. 16, this is a hexadecimal number. Now we need to convert this to binary. How do we do that? We will do the same thing that as we did before, but just in reverse. So we have to split it out. We have 4 and B. What is 4 in binary? Well, you could look at the table, or you could remember it by heart. This would be as it states 0, 1, 0. And our B will be, B corresponds to 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. After 10, we have A and B, so it will be 12, no, 11. Oh, sorry, yeah. Sorry. 10 is A, and then 11 is B, so it will correspond to 0, 1, 1. Just like that. Combine these two together, we have 0, 1, 1, 0, 0, 0. This is our binary number. Now, one more thing. This 0 you can remove because it's the least significant bit. This 0 is called the least significant bit. This 1, or this bit right here, is called the most significant bit. Let me just write its full version over here. SB02. No, not least. God, I'm sorry, I can't write. I can't write. Least. I know my handwriting's not good, but hey, you have to do what you gotta do. And I could swear that my computer is lagging. So the least significant bit holds the least value, whilst the most significant bit. I think I got those two mixed up. God damn it, I think I did. I think I did mix those two up. Yeah, pretty sure I did. This is the most significant bit. This is the least significant bit. Really sorry about that, but yeah, because this holds the most value. For instance, as we stated, where is that? Yeah, here. So this is the most significant bit. This is the least significant bit. This holds the least value. This holds the most value because 1 into 2 raised to the power 3, that's 8. Whilst 1 into 2 raised to the power 0, that's just 1. Okay. Now with that, we have this done. Sizes, as we stated before, it's just the same rule. Logarithm rule. Let's talk about that now. Let me just... Interesting, it sort of like changes with it. Let's just, again, draw a line from here to here. Let's draw a longer line from here to here. And a few things left behind. Let me just correct that. 16 E1. It's a slightly different shade, but don't worry, they're both pink. So now the logarithm. Logarithm it states, calculate the number of bits k needed to represent a certain number of combinations n. The formula is n is equal to 2k. If you need to represent 16 states, log 2, this is how you do it. So what it says is that it's sort of kind of difficult for you to estimate how many bits go into, or how many numbers, like decimal numbers, can be represented by how many bits. So let's say we want to represent, what's a random number? 27, 6 in binary. Wait, just let me use 6. Objects in binary. How many bits are required? Question mark. Well, to do that, what we will do is log to 276 and our whatever answer this will be Actually, I don't know what answer this will be. I don't have a calculator right now. But whatever answer this will be, that is how many bits are required. And if this answer, if it will be in decimals, for instance, it'll be like 3.14159. I don't think that's pi, but we have to do an operation that we call a ceiling operation, which is basically rounding up. It's just a fancy way of saying rounding up. So we'll round this up to 4. No matter like what number this is, even if it's 1, if it's 5, if it's 9, whatever it is, we will always round up. So that's how we find that out. There's one more thing which states that this user knows how to calculate bits of combinations. The formula is so we are shown let's just stop with the arrows. I think it's becoming a bit too distracting. I'll get a hold of this, after a while. It shows us that at 2k, this is the equation. What equation we used is basically the same one, we just mingled it up a little. We applied log on both sides, which got us. Wait, did we? Let me just understand this. I think yes, we did. We just applied a log to both sides and rearranged it to get this operation. So it's the same thing. I don't even know how to do this. How about we do log. We can do this. Move the entirety of that downstairs. There you go. Okay. So now we move on to lecture 2. We're done with the basics, the number division, the number systems. We have done 3: binary, hexadecimal, and marble decimal. I'm sorry, I just can't get this thing off my mind. Let's just talk about this a little bit more. This basically means that if you have 4 bits, then, and what's 2 into 4, 2, 4, 4, 8, 8, 16. If you have 4 bits equals or gives you 16 possible combinations. Now let's move on to our second lecture. A little more fun facts or notes that we sort of had to keep in mind. So, as we stated, that number systems always include 0. God, my handwriting is very bad right now. Just give me a minute. Since number systems always include 0, that means if we have 16 combinations, that includes 0. So in reality, we only have up to 15. Therefore, the equation that we had, 2n minus 1, this is the equation that is required to get the actual, numbers or highest numbers that you can represent. So if we do 2, 4 minus 1, that gives us an answer of 15. That is the highest number that we can get with this, as it states here. I think I'm going to end this here. I have a few things that I need to go to, and this was just almost lecture 1. The next lecture we'll go over the gate and a bit about system. Very long, so let's go. Okay.